Okay, so hello everybody. We have come to the almost the end of the separation processes. We have been doing this for a very long time. We have covered distillation and then absorption, then adsorption, and today we have come to extraction process. Now, what is this extraction process? In this particular extraction process, what we do is that if I can just show you once, this is basically like this. We have say one particular feed stream, right? This particular feed stream, it contains say a minimum of 2 miscible components. This is a liquid feed stream. So, therefore, this is a liquid feed stream. It has at least minimum of 2 miscible components and we want to separate it. When we want to say the components are A and B, say we would like to separate B from A. It will either be for purifying A or for recovering B from A. What do? We put it in an extractor, okay, and we add another liquid which is known as the solvent S, which is immiscible with the feed stream, and this solvent S, this is mixed up with the feed stream, and after mixing up, what happens? This S, firstly it is immiscible with the feed stream and it has a greater affinity for component A. Component B, right. So, greater affinity for component B. So, naturally what happens? Component B, it diffuses from feed stream to the solvent stream, or in other words, there is transfer of component B from the feed stream to the solvent stream. After the mixing is over, naturally how long this transfer will go on? As long as the chemical potential of B is not equal in the feed stream and the solvent stream, or in other words, mu B in the feed stream, as long as this is greater than mu B in the solvent stream, the mass transfer goes, and after the mass transfer we get two streams. One particular stream that we get, that is the feed stream depleted from the solvent. This particular feed stream minus the solute, not the solvent, minus major portion of the solute B, this is known as the raffinate stream. This was already mentioned to you when we were doing our equilibrium classes. And what else we have? We have one more stream which is the solvent stream, which is rich in the solute B, right. This particular stream, this is known as the extract stream, which contains a large amount of solvent. It contains the solute B and also it contains a small amount of feed liquid A. And this feed stream, what it contains? It contains A primarily, maybe a small amount of solvent depending upon the solubility, and it also contains definitely a small amount of solute B, right. Now, from this, remember, we have definitely removed B from A which we wanted, but again if you see both the liquids, you will find that in both the liquids what you have B mixed with both A and S. There will be more S, little A, but whatever it is, but there will be B mixed with A. So, therefore, just like for all separation processes where we add a mass separating agent, you have already done two such separation processes. One was absorption, the other was adsorption, and in both of them you have seen that solvent regeneration, recovery and recovery of the solute is something very important. In this case also we will find that recovery of the solute and also the regeneration of the solvent, these are extremely important. So, if you have just this process, which is the extraction process, it is actually incomplete. So, what we do after this, we have got two streams. Both these streams, they are sent separately to a solvent recovery unit. The extract is sent to a solvent recovery unit, the raffinate is sent to a solvent recovery unit. Generally, the recovery, it is done, the process normally in industries is that we undergo a flash distillation, maybe two flash distillations, one at under pressure, one under vacuum, and after that, if required, we go for a steam stripping or a distillation. Once we have got here, from here what do we get? We get the extract E, which the solvent has been recovered. So, we get the extract E, which is depleted from the solvent. And in this case also, after solvent recovery, we get R prime, which is again depleted from the solvent, or in other words, both E prime and R prime, they are rich in the solute that we had wanted, this solute B. Okay. And from both SR1, we get the recovered solvent S. From here also we get the recovered solvent S. So, both these then sorry, I'll just draw it in a I'll just put it on the top, not at the bottom. That will be easier for me. So, therefore, from here we get the recovered solvent, from here also we get the recovered solvent. This recovered, both this recovered solvent, they are then recycled back and they come and join the main solvent stream here, right. So, from here we get some amount of recovered solvent, say S1, from here we get the recovered solvent, say S2, both of these are joined and then the two streams, they are once more recycled. And remember one thing, in the entire process, there will be some amount of solvent losses. So, as a result, we would also give some amount of makeup solvent here, and then the process continues in this particular way. This is the process of extraction. Now, from this particular process, you can very well understand what are the challenges which are involved in liquid extraction. Tell me, what are the challenges? The first thing is, we cannot consider just the extraction, this particular extraction unit in isolation. Whenever we have to consider the extraction unit, we also need to consider the solvent recovery step. Quite often it happens that the solvent recovery step is the more expensive process, therefore, their economics is guided by the solvent recovery step, which is usually, as I have told you, a flash followed by steam stripping or distillation. Therefore, several times we find that when we select a solvent, it is more keeping in mind the ease of recovering the solvent or the cost of recovering the solvent in the solvent recovery stages, rather than its selectivity, although selectivity is also important. This is one particular thing that we have to remember. This is true for all the processes which involve separation using mass separating agents, as we had discussed in the very beginning of the introduction of the separation processes. What is the next thing which is important here, which you have to remember? After the solvent and the feed are mixed, then they are separated, the extract and the raffinate are taken away. This is done for absorption, distillation everywhere. In absorption, distillation, stripping, what are the two phases that are taken out? One is a vapor and a gas phase, or a gas phase, and the other is a liquid phase. They are having high differences in density. So, the separation of the two phases after the intimate contact, that does not present any challenge, it is just gravity separated. But in this particular case, if you see, the extract and the raffinate, they are liquids. Usually there is not a very high density difference between the two. As a result, what we find is that the separation of the extract and raffinate just by gravity is often incomplete, and therefore, this also presents a special challenge for liquid-liquid extraction processes, which is not present for other processes involving mass separating agents. Very frequently we find that gravity is not sufficient and we have to use a centrifugal force for separating the extract and the raffinate phase. In fact, I will tell you one thing, you will often find that the efficiency of the process is quite low. Normally we take as 50%, maybe maximum 70% efficiency, much less than the efficiency, the tray efficiency that we get for distillation processes. Remember one thing, this particular decrease or the reduced efficiency that we get, it is mainly for the insufficient or mainly for the insufficient separation between the extract and raffinate phases rather than the equilibrium considerations. This is something which we need to remember in liquid-liquid extraction processes. There is one other also very important challenge, if you remember, when we were discussing the equilibrium processes or the equilibrium considerations, I had mentioned one thing. For vapor liquid equilibrium in distillation, we refer to the TXY, PXY or XY plots. For gas absorption, we refer to solubility plots. All of these are 2D plots. We have a x axis, we have a y axis. Usually the mole fractions of the two are plotted on the 2 axis, or rather the mole fraction of the component which is to be transferred. In case of distillation, it is the more volatile component. In case of absorption, it is the component that is to be transferred. So, that component's mole fraction in the 2 phases are plotted as the 2 axes. In case of liquid-liquid extraction, if you see the way I have shown here, we find that it is very difficult to get two liquids which are completely immiscible with one another. There, even if small, there will be some limited miscibility of the solvent and the feed liquid. As a result, if you find what I have shown you here, that in the extract stream also there will be a small amount of feed liquid. In the feed stream also there will be a small amount of solvent liquid. Therefore, what do we do for representing the equilibrium? If you recollect correctly, we use a ternary plot, right. If you remember, I will be going into the details of this particular ternary plot, where the apices, they refer to the completely pure A, completely pure B and completely pure C, pure solvent S, and each particular arm that represents a binary mixture. So, if we have started with A and B, then this arm represents the composition of A and B. As we go more towards the vertex B, it means that the proportion of B is increasing and the proportion of A is decreasing. Now, suppose in this particular liquid, we add component S. So, therefore, maybe we had started from this feed composition and we add S. Immediately what happens? The composition, instead of staying on this particular line AB, it shifts to inside the triangle. And depending upon the composition, we find that on addition of S, the composition, it shifts into the triangle and it moves along the line which joins the feed composition to the vertex X. I have considered the vertex S under the condition where I have taken fresh solvent, or even if I have taken regenerated solvent, it contains very less amount of A and B. So, under that condition, I can join the vertex S to the feed composition, and with addition of S, the composition of the mixture, it shifts from the straight line into inside the triangle. The more amount of S we add, the more the point is going to shift. So, therefore, the composition of the feed on addition of S, it moves along the straight line, say from the line joining the feed composition to the S. The more we add solvent, the more it moves, and therefore, the proportion of the solvent to the proportion of feed is given by the ratio of it's from the lever rule. It's given by the ratio of the feed point to the mixture point and the solvent point to the mixture point. So, quite naturally, as we keep on adding solvent, we keep on moving towards this. So, therefore, this also presents an additional challenge, the ternary distribution plot. So, naturally, the calculations become much more difficult. Remember one thing, despite all these challenges, there are situations where instead of using distillation to separate the two miscible components of a liquid solution, we have to resort to extraction. Definitely there are applications, and that is why this particular topic is being discussed with you, and this particular topic, it is getting increasingly important in industrial applications, particularly with the advent of pharmaceuticals, fine chemicals, food products, etc., etc. Definitely you have to remember that with all these challenges, extraction will be opted only under conditions where either distillation is not possible. When is it completely not possible? When suppose I have say A and B, and this from this A and B, say I have started from 50% A and 50% B, and the specification is that from here I have to recover say about 90% B, and we know that an azeotrope is formed say around 80% B. So, therefore, when we start distilling, what do we get initially, and B is the more volatile component say. So, when we start distilling initially and the top product we start getting B, this is the more volatile component. So, we start getting the top product which has more of B as compared to A. We can increase the number of trays and we can keep on attaining more and more enrichment of B. This continues till we reach the azeotrope composition at 80% B. After that, we find that there is no further enrichment and we have no way of moving from a feed liquid of 50% B to an enriched liquid containing 90% B. So, there are certain things that we can do about it, which was told to you earlier. First thing is, we can add a third component which breaks the azeotrope. This is known as an azeotropic or an extractive distillation. It can also happen that we can change the pressure, and on changing the pressure, the azeotrope condition can be it can be eliminated. Under that condition also we can get this. There are situations where none of these are very possible. So, under those particular conditions where we find that that the azeotrope, it cannot, it's not worth changing, or rather if we change the pressure, the relative volatility between the two components, they do not change to a great extent, and it is also not very feasible to use a third component to break the azeotrope. Under that conditions, definitely we have to opt for liquid extraction, and some very common examples is to extract formic acid, tetrahydrofuran pyridine from water, or maybe to extract ethyl acetate from ethanol. So, for these particular situations we go for liquid extraction. It can also happen that the components, they do not form an azeotrope, but they have a very close relative volatility. And therefore, in order to effect some particular separation, we have to use a very large number of trays, okay, say 45-50 trays, which is definitely not going to be economical. Under that conditions also, possibly we can go for extraction, particularly when the conditions are such that recovering the solvent from the raffinate and the extract is not very difficult. A typical example is, say we have an aqueous solution containing acetic acid. Normally what we do in this particular case, we use methyl tertiary butyl ether as the solvent, which can be easily evaporated away, and we can recover the acetic acid from the MTB solution. Under this condition, definitely we would opt for the extraction rather than the distillation process. The same thing, a very typical example from oil refineries is that from the lube oil vacuum distillation carts, we often have to recover the aromatic compounds. And this we do very easily by using phenol, furfural or NNP, such type of solvents. There can be situations where the product that we want, that is very heat sensitive, and therefore we cannot go for distillation, it cannot withstand the heat which is going to be supplied in this case. This is more relevant for pharma companies, food industries, fine chemicals, particularly for the extraction of vitamins, penicillins, flavors, fragrances, etc. Also in chemical industries for recovering of certain aldehydes and organic acids. So, for such particular cases, extraction has become increasingly important. As I have already told you that the importance of extraction is particularly more relevant in the modern times with the importance of food industries, pharmaceutical industries, etc., etc. There are certain other cases, say separation of metal ions, copper from iron, nickel from cobalt, chromium from vanadium. In these particular cases, suppose they are there in an aqueous solution. The conventional thing that we do is we add an organic solvent. What happens? Out of the two ions, one of them that forms a chelate with the organic solution or the organic solvent, and the other remains in the aqueous solution. This is a very typical way of separating the metal ions, the precious or rare earth metal ions from one another when they are there in an aqueous solution by using an organic solvent. There is one other thing also, suppose you have got some non-volatile organic compounds in an aqueous effluent, right. Say maybe we want to remove phenol, cresol, aniline, etc. from industrial wastewater. Okay. For such cases, definitely instead of going for vacuum distillation, etc., it is much more economic to have a proper solvent which can bring about this separation. This is a standard thing which is also used in food industries when we have to remove high molecular weight fatty acids from vegetable oil. Instead of going for vacuum distillation, which will be much more expensive, we prefer to use liquid propane as the solvent. So, therefore, due to these conditions, despite the limitations which liquid extraction has, which I have already told you, the primarily challenges it has, liquid extraction is often opted for, and therefore, we will be keeping the challenges in mind, we are going to address the design of different extractors. Challenges, I will repeat once more. First thing is separation of raffinate from the extract phase. This is a unique problem which you did not face for adsorption distillation, and this is naturally due to the close density of the raffinate and the extract phase. After this, once they are separated, next is the solvent recovery unit. As I have told you, this is primarily done with flash distillation and followed by maybe one or two flash followed by steam stripping or batch distillation. So, therefore, this step and the cost incurred here, this has to be considered when we deal with liquid extraction. We cannot deal with just the extraction part alone, and to make matters worse, the ternary distribution plot definitely has to be considered when we are dealing with this extraction problems. There are situations where we can go for the XY plots. We will be discussing under what conditions we can do it. So, therefore, what are the things that we have to do? Just like in the case of absorption, we had to select a proper solvent. In case of adsorption, we had to select a proper adsorbent. In this case also, choice of solvent is the first important thing, and the second important thing is the contacting device. The first thing that we are going to discuss is the choice of solvent in this particular case. Again, we refer to the ternary plot in order to guide us in the choice of solvents. Now, there are two things also I would like to remember. When we select a solvent, it will be depending first on the solvent which will have a greater selectivity for the solute that we are going to opt, and the second thing is the solvent can be recovered easily from the solute both in the extract as well as in the raffinate phase. We will deal first with the selectivity part, the extraction part. Now, in this case, as I had already mentioned, that we represent the equilibrium in the case of a ternary plot, as I have told you. Now, as I have told you that this is the feed composition and I am using pure solvent, we assume that either we are using fresh solvent or the regenerated solvent has very less amount of A and B which can be neglected. So, naturally what we find that the feed composition now shifts along the line FS, as I have told you. Now, remember one thing, inside the triangle we have got the three components together. Now, here if you find I have drawn a dome, this zone is the zone where the A and S, they are more or less quite immiscible from one another, and therefore, within this dome the liquid, it forms two different layers. So, this is the zone of immiscibility. So, therefore, you have to remember that when we add a solvent, the quantity should be sufficient such that the point we reach after the solvent is attained, that lies within the zone of immiscibility. If we add a very small amount of solvent such that the point lies here, then in that case it is going to represent a solution containing A, B and S, a homogeneous solution containing A, B and S, whose compositions correspond to this particular point. If we have added solvent to come to this point, we cannot get the separation by means of extraction. So, we need to add solvent sufficiently such that we have entered this dome. Now, what does that mean then? Definitely it means that if we have a solvent where the dome, the zone of immiscibility is larger, definitely we will opt for that particular solvent, right. So, therefore, if you observe in this case, this is XBF, this is S, the feed composition is going to vary along this line when we keep on adding solvent. Now, we find that the minimum amount of solvent that we need to enter the zone of immiscibility, it is say Q prime in the first case, and maybe for the solvent 2 it is say it is Q2, say this is Q1, Q2. Naturally, we find that if we opt for the solvent which is represented by this zone of immiscibility, then we need a greater amount of solvent that has to be added here. So, naturally, if we are given these two solvents, we would definitely opt for the solvent 1 with the zone of miscibility which is given here. So, this is one comparison. The other thing also, remember that this particular zone for the same solvent, it is influenced by temperature, and as we increase the temperature, the liquids, they get more and more miscible. So, therefore, with increase in temperature, we find that the zone of miscibility shifts from the this zone to this zone. So, naturally, what does that imply? That we would always like to opt, or we would always like to perform extraction even with the same solvent at the lowest admissible temperature. But at the same time, you need to remember, when you are going for a lower temperature, the rate of mass transfer, that the rate of diffusion, that decreases. So, therefore, we have to optimize on such a temperature where we get a sufficient zone of immiscibility, and also keep into mind a sufficient rate of transfer, so that we can optimize a better efficiency and a better throughput, and we can perform the extraction process. This is point 1. The point 2 is that, well, we have added solvent, we have come into the zone of immiscibility. Say now we are at a point M. What is the solvent that we have added? We have added this, the ratio of the feed to the solvent is quite naturally Fm by Ms, right. Perfect. After the extraction has taken place, then we go for a recovery stage. So, after once we have added solvent and it is in this particular M point, definitely this lies within the zone of immiscibility. So, therefore, it separates into two liquids. the raffinate phase and the extract phase. Now, if you remember, both the extract phase we had sent it to a solvent recovery unit. When we send it to a solvent recovery unit, if we assume that the entire solvent has been recovered, then after that what is remaining from the extract, the E prime that I had shown you, E prime means that portion of the extract from which the solvent has been completely removed. So, naturally that lies on this particular point, right. From the raffinate also we remove the entire amount of solvent. When we have removed the entire amount of solvent, then in that case the raffinate point lies in at R prime. It is quite evident now that the further away R prime is from E prime, the better is the solvent. So, we would always like to opt for a solvent which has a greater difference between R prime and E prime. So, what do we do for that? We take different solvents, we try to plot these ternary plots, the feed composition is fixed. We take the same proportion of the solvent which is denoted by point M, or we take the same proportion Fm by Ms, and then we draw the ternary plots. We find the difference between E prime and R prime, and then the solvent which gives us the greater difference between the two, we naturally opt for that particular solvent. There are certain additional considerations, of course, that is denoted by higher selectivity and larger immiscibility envelope. There are also certain other considerations that we need to consider. We will be discussing them before ending this class. First thing is, it is very evident that there has to be significant density difference between feed and raffinate throughout the operation range, so that we can get a proper separation between the two, and before the raffinate and the extract, that can be sent to their respective solvent recovery units. That is a must, I have told you, and often what we do, we employ centrifugal separation rather than gravity separation in order to bring an effective separation between feed and raffinate. And I have also told you that the reduced stage efficiency is also due to inadequate separation rather than the equilibrium considerations. Next thing is what? Low interfacial tension. Remember one thing, when we are going for extraction, what do we do? One of the phases that gets dispersed in the other phase. So, therefore, if you want a proper mass transfer, definitely the phase which has a higher mass transfer resistance, that has to be broken down into large number of droplets. So, therefore, the smaller the droplets, the better will be the mass transfer. So, therefore, lower the interfacial tension, the smaller we will be getting the droplets and better will be the mass transfer. So, we would always like to opt for a low interfacial tension. Here also I would give you some particular caution. See, suppose the droplets, they have become very fine, very emulsified, then in that case coalescence becomes a problem. But after the extraction has occurred, we would like the droplets to coalesce and either settle or rise depending upon its density relative to the continuous phase density. So, therefore, we would not want to have a very fine droplets, at the same time we would like a proper emulsion. So, therefore, a more or less low interfacial tension is necessary. I would also like to mention, normally data on interfacial tension is not available. So, therefore, we often what we do, we denote the interfacial tension as the difference between the surface tension of the feed solution and the solvent. Well, there is one other thing, low viscosity. On this we will be discussing much more. At this moment it is sufficient for you to remember that naturally when we have a low viscosity, the pumping power will be less. We have to pump the solvent into the extractor, pumping power is less, extraction rate is higher, heat transfer is higher, it is easier to handle. So, we would always like to go for low viscosity. Of course, on this point we will be having some discussions later. Well, after this the extraction part, we go for the solvent recovery part. There what we need to remember, there should not be any azeotrope formation with respect between the solute and the extract, or rather between the solute and the solvent, and there should be a sufficient high amount of relative volatility to facilitate solvent recovery. We would also like to have a solvent which remains liquid over a large portion, or in other words it has a high boiling point and a low freezing point. Again, when I tell you this, you have to remember, definitely we would want a higher boiling point or a lower vapor pressure for ease of handling and storage, but at the same time we have to remember that we are going to separate it from the solute by means of distillation. So, naturally we, for that particular considerations, we would not like a solvent with a very high boiling point. So, here also there has to be a compromise, right. And most of the cases what we do, we select a solute which has a high selectivity. So, the extract phase that we get, that has a large amount of solute, a lesser amount of solvent, and it is easier to vaporize away the or distill away the solvent. So, naturally there has to be a compromise such that the solvent can be distilled away, it has a sufficient alpha, the relative volatility difference with the solute. At the same time, we would want a solvent which remains liquid for a larger portion. The other things that they are common to all particular solvent selection for different operations. I would not like to go into the details of this. So, once you have realized the challenges of liquid extraction, you have realized that based on these challenges we are going to select the solvent. So, therefore, after this we will be going for the contacting devices. We will take up the simplest contacting device, simply a mixer where we mix the two, we agitate it, and then the extraction occurs and then we separate it. And once we have discussed this, we will go for continuous operation systems. So, for the moment this much only. Thank you very much.